Hello everyone, let's talk about computer science algorithm depth first search. Um, it is about traversing the graph in an aggressive way. That is like we go as deep as possible, and when we run out of all the options, we actually backtrack and then retry the same thing again. So that's why it's like focusing on depth, and we will see the example how. And it can be solved iteratively using stack. We will first discuss that. But if you if you have seen in computer science, there are many times when we see a stack, it can be also solved in a recursive way, and actually recurs, and that's why we also talk about recursion stacks and those kind of things. So let's jump into the dry run of this problem. So we have this sample graph where we have five vertices in it, or five nodes in it, 0, 1, 2, 3, 4, 1, 2, 3, 4, right? And it's an undirected graph, but we can also do the same thing for the directed graph. And the idea is that we maintain something called like a visited set and the stack. Of course, they look like what do you say array, but actually they are more than that. So it's like stack is like this will be the top of the stack, and set is again internally be an array, but it has the good property that it has what is the time complexity of inserting and getting the element is O of 1. So now let's jump into the algorithm. So what we do is like we first need the starting node. So suppose we choose 0 in this case, but sometimes we are also given an initial index or initial vertex. So what we do is like we first insert 0 into the stack and also the visited part, because what 0 in visited signifies is that we have seen this node, and what 0 in stack signifies is that we have to now process this node. And if you see, I have marked 0 for the case where we have visited so far, but we have to also now start processing it, and blue for the case where we actually process this node completely. So what we see is like once we insert into the stack, we check if the stack is empty. The answer is no. So we will pop out the vertex 0 because it's at the top of the stack, right? And this is the only element. And then add all the non-visited adjacent vertices to the stack. So in this case, we will add 1, 2, and 3 to the stack, and also to the visited list, because now we have seen them, and but we have not yet processed them, so that's why they are into the stack. And as 3 is at the top of the stack, you can see here, we have to now pop out 3 from the stack. So we will start with 3. um, we process it now, and we see, are there any adjacent nodes for 3 which are actually not yet visited, and the answer is no. So in this case, we will not add anything to the stack. Then we pop out 2 from the stack, and make this also as processed. And now we also see that, okay, is there any adjacent node for 2 which is not yet visited? And answer is 4. So we will add it to the stack here. Let me move this here. I think this is blocking the way. And once we do this, then we pop out 4 because that was at the top of the stack, and uh, mark it as process because there is no non-visited adjacent set next to it, adjacent element next to it, which is not is in the visited. And then we pop out 1, which is the remaining element in the stack. And again, there is no element next to 1 which is still not visited. So that means our we don't have anything to add to the stack, and now the stack is empty. So our traversal has been 0 because we first process 0, then we process 3, then we process 2, then we process 4, and finally we process 1. So our DFS traversal is 0, 3, 2, 4, 1. Of course, it does not have to be the same. It could have been the case that when we were inserting 0 into the stack, at that time we could have also inserted, like instead of inserting 3 at the end, we could have inserted 1 at the end. and then the traversal would have changed a bit. So they are not always unique. And now let's jump into the recursive part. So we are again using the same graph with four, I think five vertices, and from 0 to 4, and we just use the visited set for now because we don't have to use stack, and we can just use the recursive stack. So the idea is again the same. We push 0 to the visited one, as well as now we what we will do is, like, we will look for all the all the non-visited adjacent nodes for this one. So in this case it will be 1, 2 or 3. So suppose we picked up 1, right? And we will just do the call the DFS recursively again, and we have mind you, we have not completely processed the node, so that's why I have not marked this as done. So now what will happen is, like, we will go to 1 and add it to the visited as well. But now we will again look for, like before processing it, we have to look for, are there any adjacent node which are not yet visited for 1, and the answer is yes, it is 2, right? So we will again add 2 to the visited one, and move ahead further. So now what we will see is, like, we will look at 2 and look at again, are there any visited node which are there any nodes for 2 which are not yet visited? So we will see that, okay, 0 is already visited, so we will not go there, but we have not visited to 4, so we will also add 4 to the visited set, but none of them is yet processed, right? Because we are going deeper and deeper and deeper. So this is what this algorithm is showing now. Now we are here, so finally we will see 4, and we will see, are there any visited nodes, non-visited nodes for 4 which are adjacent to it? And the answer is no in this case. So that means now finally the 4 is processed, right? So we will recursively backtrack. And when we backtrack, where will we go to? We will go to 2, because 2 was a node from which we called DFS for 4. So now we go to 2, and then we will see, are there, like, 2 is already visited, right? And are there any nodes for 2 which are not yet are there any adjacent nodes for 2 which have not yet been visited? Then the answer is again no, right? So that means 2 is also processed. Then we backtrack, and this time we backtrack to 1, right? Because we came, if you remember, we came from 1 to 2 here. Now we are going back to 1. So this is what backtracking means. Now when we are at 1, we again check, is there any node adjacent to 1 which is not yet visited? And answer is again no, so that means we have processed 1 as well. Then we go back to 0, and we this time we again look for all the adjacent nodes for 0. Are there any nodes which are still not visited? And the answer is yes in this case, because we which is 3. So we will add 3 to the visited set now, and then look for all the adjacent nodes which are not yet visited for 3, and the answer will be wrong, like no. So 3 is also processed, and eventually in the end 0 will be the last node, so we will recurse back to 0, and there is no adjacent node for 0 which is not yet processed, so we will just what you say, mark this also as processed, and color it blue. So the efforts traversal for, in this case, for us will be, if you remember correctly, it will be 0 1 2 0 1 2 4 3, because it depends, like, how, when you process. So before making DFS call, we can always add to the DFS recursive list, and then mark it as what you say, open for processing. So now that we have covered both recursive and iterative algorithms, I think we can now start using them in multiple coding challenges that we will be seeing in Lead Code and other sites. Also, the code for both the approaches is available on the website. I'm not writing it here because I can't. Of course, I can write it and test it, but I think it will be monotonous. But I think I will say the concept is more important, and we will be seeing more examples of it in the coming days. So till then, please like and subscribe the video. Have a nice day.